Hello and welcome to KIM-1 Resurrection Part 3, Building the Analyzer. This is the story of getting the analyzer to work. On the board I pre-tinned all the points for the microcontroller and stuck on some lovely sticky flux that holds them in place. Now I had a cunning plan with this regarding a couple of magnets to hold it in place while I soldered it. Because the solder was already there, you need to press down on the pins to make sure it picks it up. So I thought a couple of strong magnets either side would work wonders. But unfortunately they didn't stick too well and it moved around. So I ended up just doing it with my finger and trying not to burn myself. I've speeded this up because there's quite a lot to it and it's, well, quite boring really. Bit of trouble getting it lined up. Once you get it all lined up, first of all, then the rest of it should be quite straightforward. So yeah, I've got it lined up. I'll blobbed a few pins, but I'll clear the solder off them later. Oh no, it's not quite lined up. I was doing it with the tweezers because it was getting hot. There we go, lined up all the way round. Now we'll start soldering each pin individually while pressing down on the processor to push the pins down onto the solder. Didn't need it on the first row, there was plenty of solder there. And turn it around. And again on the other side. Pressing down with them now because it was starting to get a bit hot and burning my finger. The flux I used on there was nice and sticky and held everything in place. And we go down all 100 pins, all 0.5 millimetre between them. And the other side. Those blobby bits I'll clean off later with a bit of a solder sucker and a bit more flux. Then when that's done, a bit of alcohol on there to clean off the flux because that sticky stuff does leave it sticky, so you need to clean it off. There was a few little bits caught inside and I managed to scratch the track cleaning them out, but it's only a prototype. Just get it working. See, I've lifted a bit of, well, I haven't lifted the track, it's a bit of the mask over the top that's gone. And now we zoom in and check that all the joints are okay. Always pay very close attention to all the joints. Generally go over them all and examine every one. Make sure there's no little bits stuck in there. Now I started to solder on the components, putting the solder flux on to put all the other rest of the components on the board. This all seemed to be going well until it started playing up and putting out flux and not solder and becoming very stiff to press down. And got to this stage where it's playing up. And lo and behold, I managed to snap. There we go. Snapped it clean off. So everything stopped until I could print a new handle. As you can see, I've reinforced it several times where it's been broken in the past. Not reinforced the actual handle itself, it just changed the STL file to make it larger and then reprinted it. But I was pressing very hard on this one, so I thought I'll just make the same handle again. So there's obviously something wrong with the solder paste. Here's the part that I'm going to actually print. I had the file already at hand, so just a matter of turning the printer on and sending the file over. And while that's going, I should take apart the old one. So most of it's okay, it's just that handle on the top that needs replacing. There's no point trying to glue it because it'll just snap again. I've tried that before. I've got a new tube of solder paste fit in there. You have to check the depth because sometimes the little bits on the side stick out and you have to trim them down a bit to fit. And that mauve part I just put in there, that's just the piston inside pushes in. I've got several of those at different lengths because you end up with the handle moving all the way down to the bottom and you haven't used all the paste up. That's the little lever that pushes it. And that's obviously a weak point where the screw goes through. So that's all printed up and put back together. You notice it's mauve this time. And start solder pasting. I cleaned all the other stuff off. Now this stuff was a lot easier to come out of the tube, and the old one had basically gone solid. And I checked the other one that I had the same as the old one, and that was solid as well. And then I looked up how long ago I bought them. It was 5 years ago, so I'm not surprised it's gone off. So this tube here is only a few months old, and so much better. In fact, it was flowing a bit fast and putting a bit too much paste on the board. Generally, you can get away with that and just have to clean it up a bit. So what I'll do is I'll put a smaller nozzle on so it doesn't screw it out so much each time. Go around, put all the components on, lots of resistors and capacitors. And here's the 974 AC 573s. And then put it on the rig to hold it up in the air while I use my hot air gun to solder everything in place. Now what you can do here is if any of the solder goes a bit blobby, if you're careful, you can get your tweezers in there and clean off a bit. So you see this little blob there on the third leg? There we go, cleaned it off. Now, there was too much solder. As you'll see on the close-ups later, you see there's a little bit too much solder on there. So here, on one of them, there was a bit of solder that went underneath the chip and went hard and stuck in place. I think it was mostly held in by the flux. So you heat it up a bit and poke it around with something nice and pointy like those small tweezers. And it'll turn these little balls, and if they're floating around, you can then just tap the ball down pretty hard on its edge and it flicks them out. And you see, well, one of them had gone there. And I just worked my way around cleaning any bits out. There wasn't too many, but as you can see, there's much too much solder on there. But it's just a prototype, so as long as it doesn't short out, that's fine. So here we are with the board finally assembled. I've put all the pin connectors around the side, fitted on the comms module. That's just a eBay bought serial to USB connector. We don't use the 3.3 volts off this to power this processor because I don't think it could supply enough current from the little regulator on board here. So we take the 5 volts, which I believe is coming straight from the USB, and put it through our own 3.3 volt regulator to supply this chip. And these others all just run off the 5 volts that are coming down the USB bus. So all we've got to do now is program this with the software I've written and see if it will work. So this is the code for the microcontroller on the Analyser. I've temporarily put a bit of code here just to loop around and around, turning one of the I/O ports on and off. I used one of the programming ports because it comes out to a nice easy terminal to get to. So we need to program the actual board. So where are we? Let's build the project. And well, that built okay, so now I've got to program it. Now we plug this in pin 1 to pin 1. Can't plug it in the top because somebody put some pins in the way. I'll stick it in from the bottom. Pin 1 to pin 1. It'll be powered by this to program it. I've set it correctly. Switch back to that one. And to program it, program device for production. Here we go. And raise the old program. Figure in the memory, and there we go, it's programmed it. Plug that, and that should be all programmed, ready to go. Famous last words. Now a little program here I've written. And open it first. On there. And we run it. And this, I can set how many channels it is, what mode the triggers are, positive or negative edge, the different sampling speeds, and what COM port it's connected to. Now I can arm and disarm it from here. And I've also put this false bit in to force it to transmit data if necessary. So what comms port it's on. We are on. And we're not connected. Because I haven't plugged it in. Let's just plug it in. And it should come up with the comms port. A little light flashing, and we're on COM port 3. So there we go. That's the name of the little circuit board. to do the comms. COM3. So select this to COM3. And, well, is it talking or isn't it? I'm sending data to it. Sending it to configure to do things. But it doesn't seem to be... Oh, of course it isn't sending anything back. This is in test mode, isn't it? Oh, full. Okay, let's go back to here. Put the oscilloscope on it. Right, click that on 0 volts there. And what I'll do is I'll use the other probe. So I don't have to worry about the lead in the way. Lead off. Oops. I can just poke with this lead. Oh, I have to move it over a bit. The oscilloscope's not close enough. Still in shot. Yep. So we should be on one of these ports. Was it that one? Apparently, oh, well, that's free running. Is it that one? Nope. That one? Nope. That one? Oh, got something on that one. Right, okay. I can't remember exactly which port it is. Let's bring the oscilloscope up on the screen. That's that one. Is it running? Are we going? Yep, we're running. Let's switch screens. You can see what's going on. There we go. There's my oscilloscope. It is actually a proper oscilloscope. This is just a USB connection to it. There we go. We've got a pulse going on and off. But is it going off on and off at the right speed? I'll wedge that in there. Bit of a tight fit. I'll have to reach with my hand. I can't change the settings on the oscilloscope from the software. I have to do it physically. What are we running at? Oh, right. Now that's a... Oh, that's my hand resting on it. No, it isn't. Why are we getting such a strange shape? What frequencies are we running at on that? Right. If the cursor's over on the screen. There's no cursors on the screen. Oh, great. Just do a single grab of that. There we go. I don't think our cursor's over on the actual oscilloscope. They're not shown on the screen for some reason. We've got a frequency of... where are we? 20 hertz. Right, that should be 500, not 20. That means we're running a bit on the slow side. I think the clock settings haven't worked properly. Okay, so a little bit fiddling with the software later. And we've got 49.7 millisecond cycle time, which is 20 hertz. Yeah. So we'll do a bit of analysing on here. And I'm worrying about these funny bits here. Why is the voltage jumping at these points? Something weird going on. First of all, let's sort the clock out. So here's the bit of code. It should be just looping round, waiting 1,000 microseconds. That's 1 millisecond between each loop. I've got a delay elsewhere in the sequence, so I'll just tell it to wait 1,000. Comes back and then toggles the bit output, which it's doing. So that's running on off on off on off. But instead of coming out at 500 hertz, because that's 1 millisecond cycle, and it's on and then off each cycle, so it comes out at 500 hertz, and we're running at 20, so we are 25 times slower than that. So it should be 200 megahertz on the clock. So we're doing about 80 megahertz on the 8 megahertz on the clock. Right, that adds up. That means we're running on the base clock and all the clock switching, which is all back up here somewhere. There we go, that's where we come in. And this is all the clock switching part of it, which is all totally different from the previous microcontroller I worked on. They're both the 16-bit ones, but the other one that wasn't a DS PIC 33, it was a PIC 24. And microchipping in their infinite wisdom decided to change all things around and use different registers and all sorts. So the clock switching isn't working. I wonder if it's something to do with this wait for it here. I'll have to go through this code and come back to this. This is the clock switching block diagram in the data sheet for the, I'm using a 33KC256MP308, same family. So this is the clock switching bit. So we've got 8 megahertz coming in, and for some reason we've got 8 megahertz going out. So all this bit here, this phase lock loop, etc., isn't working. And the last project I spent ages trying to get this. Oh, the other 64 channel analyzer is where I spent ages trying to get this bit to work. And looks like I've got to do the same again with this one. After a whole day of searching, this is what I found. Now here is the clock source within the microcontroller, and I'm using this fast RC oscillator at 8 megahertz. That feeds through to this circuitry here. Now I wanted to use the signal coming in here through the phase lock loop and out through here, and the signal comes out here to the clock signal. You notice there's a divide by 2 there and a divide by 2 there. So whatever signal comes in here gets divided by 4 before you get to here, which is the actual how many MIPS you're running at. So if running at 8 and it gets divided by 4, then that should be 2 MIPS. And I was actually running at 4 MIPS. So it says I'm not coming through there. And I'd look around some other bits, and that signal there also gets fed through here. And this signal coming out here is just divided by 2. So if we've got 8 coming in here, divided by 2, that gives you 4. Or you could be coming in this way. Well, I had to play around with lots of different settings. And I fiddled around with these dividers here, and I was able to make the clock go up and down. So I knew I was coming through this route here. So this bit was not getting set correctly. This is your clock source selection. When we come further down, this is the page I showed you earlier, we weren't going through any of this at all. And the thing that caught my eye, I'll find it further down, while reading through stuff, is, you see there's lots of it, is this note 2 here, which is on fast RC oscillator with divider. Now this is the value I'd been changing, and it had been changing the clock. So I'm on source 7. And note 2 says, this is the default oscillator mode for an unprogrammed, i.e. erased, device. Well, these settings, to start with, are set in the configuration bits. Well, then add a nose around in the programmer here. Let's see if I can bring the page over so you can see the bit I was looking at. And here are all the control bits up here you have to set. And when you set them, it generates some code, some source code, which you then have to paste in here into your actual source code before you compile. Well, these bits. Well, then after nosing around a bit, I spotted this icon up here, which is read the data, read device memory. So I read the memory in, and lo and behold, these settings hadn't changed. You see how that says there? That is the wrong setting. That's not what I was asking. Here, where is it on here? It's... there it is there. I'm asking for just the RC oscillator. And it's not. It's RC with divide by N. Well, that twigged me. The configuration bits were not getting programmed. And a lot more fiddling around, and all of a sudden it programmed them. I don't know what I changed. I know I redone this and repasted this into the source code, but it suddenly started working. So it was this programmer, the MPLab IDE, didn't program it. It is probably a setting that I didn't configure properly. When there's so many people using this software, the software's got to be working. I was doing something wrong here, and it wasn't configuring the bits. So all my clock code was fine. There's nothing wrong with it at all. It's just the original configuration bits were wrong. So the clock code is where I've played around with it so much, is now quite short and neat, and that's just a bit for actually programming it, because there's special locks on it. You have to use their code. So, we're up and running at the right speed now. Instead of coming in at source 7, we're now coming in at source 1, which is the clock coming in here, goes through the phase lock loop to multiply it up, it's divided down again, and out here we're now running at 100 MIPS, as we should be. When I was designing this, I was hoping to get away with not actually tying down any of these inputs. The idea being it gives me a nice high impedance input. But alas, while I had it on the bench power supply, I noticed I had bench power supply plugged straight in here, so I didn't have to have the USB port plugged in. I noticed that the current draw was going quite high, sometimes as high as 1.5 amps, and it varied whenever I touched any of these pins. I came to the conclusion that the inputs here, because they weren't tied down, were floating part way between on and off, and it's causing a high current draw, and all these ICs were starting to get warm. I had to put resistors on each channel, so 100k resistor on every input all the way around. Fortunately, it seemed to line up nice and easily, and wire around there, convenient 0 volts there, to tie them all down to 0 volts, and we went down to 49 milliamps, I think it was then. So I'll have to modify the Gerber file for that. They're all tied down to its 100k input impedance now. I tried getting away with it, and I couldn't. So the rule there is tie down your inputs. Well, I put the software in and got it running, and transferred the data across to PulseView. And I noticed when we was putting some signals on here that they were coming up on the other channels as well. And the loading before that software was running was about 49 milliamps. It's now about 160. And these 4 chips up here are starting to get a little bit warm. And so I put a temporary bit of software in here just to do the selects as we go around to see whether they're selecting. So it should be on this one for a millisecond, or a short pulse, then on this one for a millisecond, and then this one, and then this one, and then this one, and just keep cycling round. And I'm going to measure some signals in here to try and see what's going on. I suspect that more than one of these chips is answering at the same time. I mean, these two should be in pairs, because that's like the low byte and high byte. And I suspect these are coming on at the same time as these, and that's why they're warming up. Now if we stick the scope on this and see what we get. So I've wired it up to my bench power supply, and we're pulling 198 milliamps, which is wrong. Program with a probe now. So the first chip select. There we go. It's a negative pulse for the select. So we've got 3.3 volts here, and then down to 0 volts for a select. And that pulse there should be 1 millisecond. And if we move down to the next one, that's the same one. And the next one, oh, what's this? This is just under 2 volts. And no pulses. That should be pulsing. Let's just check the others. Third chip, that's the same, because that's the same chip select 2. Or output enable, I should say. And then to the third one. Oh, there's a third one, okay. That's chip select 2. And there we go. And the final ones. Yep, that one's okay. And that one's okay. That's chip select 4. So that is getting stuck halfway for some reason. I'll put the other trace on. You can see what it should be like. Red one is what it should be like, and the yellow one's stuck in between. I'm not sure why the red one's spiking like that. We go back to number 1. So we've got yellow and red, that's channel 1 and 2. That's chip select. Oh, come on. Bit fiddly. There we go. Chip select 0 and chip select 2, that is. And they're both correct. completely out of phase of each other. I'll go over to number 3. Again, there we go, that's okay. So, this chip select's not working. Go halfway. Oh, these pins are so small. Now it's on the red channel this time, so it's only 2.5 volts stuck there. And the chips are warming up. I think I'm going to have to start taking bits apart. Trying to see what's gone wrong. Let's flip back to the other camera. Alright, so I'd say I've lost my pointy stick. So I was measuring on the output enables, which is pin 1 here and here. So these two should be on at the same time. This is channel 0, channel 1, and that 2.5 volts was on pin 1 here and here, which is the output enable for these two chips. And I did the same for them. But these ones stuck part way. I did earlier measure it over here as well, and it's on the output pins there, which, well, you'd expect that. So either this is not putting out the right voltage, or something else is interfering. So what I shall do is, well, not that chip, this one and this one. I shall lift pin 1 here and pin 1 here, so it doesn't actually select these chips at all. I should really need to tie that. Oh, yeah, tie it up to positive to hold it off. I'll disconnect them and see what happens first. So I'll do just this one, and if there's no difference, then I'll take that one off as well. Although I had a measure around with the ohm meter, and one polarity it's all open circuit, and another polarity I get between this pin here, well, between all the output enables, I get 45k to all these data lines. Well, all those ones as well, which is odd, but those ones are working, so it might be a red herring, and it only works with the meter leads around one way. If I turn them the other way, it says everything's fine. Let's take those pins off and see how we go with that. Well, I lifted the legs, as you may difference, so I've completely taken the two ICs off. I didn't find anything shorting out or anything underneath, so let's test it how it is now. Alright, that's chip select 0, chip select 1. Oh dear, that's what's coming out of the microcontroller. I have to have a closer look at the actual pins on that, and they're real tiny ones. Great. Goes direct onto the microcontroller pin. And that's what we got there. And the one next to it is good. So either it's what's coming out of the board, or something on the board causing it. I'm going to try and lift the leg on the microcontroller and see whether the signal comes out of the microcontroller okay or not. That's going to be really difficult. Now lifted the pin off the microcontroller and see if I can get on that. On the actual microcontroller on its own, we get 1.5 volts out of it. So it's the actual controller that's gone wrong. Looks like I'll be soldering in a new one and see if that'll work. This has been a hell of a job getting this working. I replaced the processor and the I/O chips, and it was exactly the same. I found out what the fault is. I'll show you in a moment. There's chip select 0, chip select 1, working lovely. Chip select 2. And chip select 3. All working exactly as it should do. And pulling 129 milliamps. Alright, let's just quickly switch over to here. Now this is the data sheet for this processor. And you've got this here. Now this is to do with the oscillator. Port B1 has a function. It can either have the oscillator out or it can be used as an I/O pin. Well, so if this configuration bit here on this oscillator configuration file, if it's set to 1, the oscillator clock will be put out on that pin. If it's set to 0, then it will be used as an I/O pin, which is how I want it. So in the configuration, we go, oh, here we go, set it off, turn it off. Oh no, this is configuration bits in C. You have to do them in C. Putting it in the actual assembler won't work, has to be done in C. So what they've got here, oscillator I/O function off. Well, what that means is the function is turned off. It doesn't mean the bit is turned off. It means the bit is turned on. Because all I did was that, recompiled it, and lo and behold, are we? Oops, wrong one. Lo and behold, this bit here turns into the I/O bit and works perfect. So I've just spent all day chasing down this fault that isn't there. It was a bad configuration. I've taken 3 chips off, I've put 3 chips back on, I've changed the processor, and there's nothing wrong with the old one. I'll clean it up and keep that. But oh, what a fiasco. All because the datasheet here contradicts itself with what the C part of the programming is. That's why I hate programming in C. It's, oh, what should it be on or off? Yes, before you say it, go and look through the INI file that goes with it, but I shouldn't have to do that. I should make it easier. I'm not so stupid. Right, so back to the testing of the data coming in now. Hopefully that works better. Here we have the finished board, all set up for testing of the input. So I plugged it in USB port, it's come up as COM3, and I've put my signal generator on it, which is set at, oh, get the line on it, 1 megahertz at the moment. So we're feeding 1 megahertz straight in there. Now if we bring up, this is the software for grabbing the data off it. So let's select 16 channels at, no, select the correct COM channel to start with. Then we'll say 16 channels, 12 million samples a second. The triggers all work on this, I've tested them all okay already. So I'll just do a manual trigger on this. There goes triggered. Transmitting the data. There's a nice bright LED here to show you it's transmitting. And now it's doing the conversion to the comma separated values. And that's all finished. So if we now load that into here, import, there's the file, open, and then just OK, and it imports it all. And if we zoom in on it, there we go. So if we're 1 megahertz at 12 million samples a second, there should be 12 samples for every cycle. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go, and then we cycle again. As soon as we're at 12.5, there will be a slight stutter in it. You'll see that bit there is slightly longer than that one. And that's because we're sampling at 12.5 there. So there's 1, 2, 3, 4, 5, 6, 7 samples there, and there's 1, 2, 3, 4, 5, 6 on that one. So it's because we're slightly off on the sample rate. We bring that down to 4 million samples a second, and we just do a trigger again. So I'll just do a manual trigger because it's easier. Just for the test. And we go back to here and we load that one in. Oh, there. Okay, there we go. So it doesn't take long to get the samples across. So this is 4 per sample. Notice here we've got 3 and 1, still the same rate. We obviously got a bit of alias in because we're only like at 4 to 1. You should really sample a bit faster than 4 to 1. We go to here, we change the frequency. Let's drop it down to, let's do 100 kilohertz instead. So it's 10 times slower on the pulses. And we trigger that again. So I could link the trigger across to it, but it will trigger instantly as soon as I set it. So I'm just doing it manually. And we can sample that. Let's bring that back in. Where is it? And we zoom into, there we go, 10 times as many samples. I've yet to find out how to set this speed up here. Tells you what sample you want, but it'd be nice to have that in time based. I'm not sure if I can do it on these comma separated values. What's nice about using the comma separated values is it puts all your data here. It tells you how many channels you've got. If you just use the raw data, because I can load in the raw data, import raw data, and that's this one here called test raw. You have to tell it how many channels every time, otherwise it will read the data wrong. So there, you can read the raw data in if you want. There is the facility on here to just do raw data only if you wanted. It's a little bit quicker. That takes about 6 seconds, and with the conversion it takes about 12 seconds. You notice these buttons over here are slightly different from earlier in the video. There's obviously ARM for army, whatever state, you set your ARM, and there we go, it's waiting for a signal, gets a signal, and it'll grab it. And then there's a disarm, say, oh no, don't do that. Resend is in case something goes wrong in the transmission, the data's still sitting in the analyzer. Doing a resend will just send the data again, or try to send it again if it failed. Like if your comms port fell over or something, you could reconnect and send it again. Pulse view itself has a habit of crashing, or sometimes it doesn't close the file that is imported, and then you can't save because the file's still open, so you have to shut down Pulse view and open it up again. That's when you'd use this resend signal. That's a problem with Pulse view. It's a little bit flaky, but you can't complain seeing it's free. If you select, say, the wrong comms channel, it tells you that the comm's not there, won't work. You just go back to the correct one. Sometimes you have to click twice. There you go, comms channel opened, okay. We're talking again. And you just select whatever speed you want. We're pretty much all ready to go for fixing the KIM-1 now. So I hope you enjoyed this rather long video. And don't forget to like and subscribe, and I'll see you in the next one.